Okay, we talked a little about Linux philosophy and GitHub. Let's go over to a compilation. How do we actually compile a program? What did y'all use? Just Eclipse and NetBeans and hit build and it just magically did it? Okay, all right. It'll be a little more complicated here, but not too much, or hopefully not much more. We're going to use GCC. Actually, we're going to be using G++ in this class. Hopefully, we'll have some time to talk about the debugger, which are very helpful, but I have a hard time convincing students to use it. We will be using make. I have an easy time convincing students to use make because it makes compilation way easier. Valgrind I've had some success with. It helps really point out your memory bugs for you. We'll talk about GNU Plot next time, and then we may get to perf, which will tell you your performance issues inside of your program, aka what functions are taking the longest amount of time, or which is consuming the most amount of time in your program. All right. Okay, let's go start with a simple program. Sure, let's jump over here. day02 compilation. All right, test.c. So I'm going to start with C, even though I believe most of y'all in, what was it, procedural, used C++. Is that right?
Yeah.
Did y'all do G++ or did y'all do like a different compiler, MSC or ICC or something?
G++.
All right. So this is C++, or C code, I should say. All right, so I've written it. I do gcc test.c. If it doesn't do anything, that means it succeeded. Or it doesn't tell you anything, that means success. Well, what did it do? Let's do an ls. Oh, we have an a.out file. So originally we had test.c, now we have a.out. So I did gcc in order to compile it. For this class, we will call it compiling. Keep in mind that it's compiling it, assembling it, and linking it all together for you, but we're just going to call that process compilation for now. It gave an a.out, and then we can run the a.out, and then there's hello world. Okay, great. How are we doing? Good so far? Well, if we didn't want to call it a.out, we could do gcc test.c and call the output a.out. The .o tells GCC whatever it is you're doing, not just compilation. You might be doing something else with GCC, by the way. Whatever it is you're doing, dump the output to a file called a.out, or in this case, I'll just call it test. And now I can run test. For those of you in the Windows world that really want to have the extension, yes, you can call it .exe, and it'll do the same thing. Again, in Linux, the extension is meaningless. And Linux will try and do what it can just by opening the file and inspect it. So I can do file and test.exe. And, ooh, yeah, look at all that. ELF 64-bit pi executable. This is the only word that probably matters for now. The rest of it, don't worry, we'll get to in operating systems. Ooh, it has pi. All right, you can do file test.c. And it even tells you it's a C source code file and it's ASCII text. All right, see, get up here. All right, good. And we went through that, perfect. Okay, we'll get to -G in a moment. What -G tells the compiler is to add debugging flags or debugging information. This will be very helpful later on. When you have an error, you have no idea what's going on, -G will put in some information so that when you get it, it'll say, hey, look, this is the line of code that caused the problem. One thing to keep in mind is it does make the file size bigger, so we do -L on test.exe. What is it? Just over 16K. So we do gcc-g test.c. I'll call the output test.debug. Notice now, okay, this time it was only slightly bigger. That's good. I've had situations where it will easily double the size of your binary. But just keep in mind that there is a bit of a difference size-wise. There is also other things that are added, and if you want to get rid of all of it, you call the strip command. I'll put it on the debug. Hey, it's even smaller than the original exe now. Of course, now you don't have any information in it, but that's fine.
No information, do you mean it's like empty?
Okay, sure. One moment. objdump-d test.exe. You ready for this? Oh, here, look at that. I'll even pipe it to less for you. All right, so this is the contents of the binary. Hey, look at that. Interp. Here are the assembly commands. See, do we have some data files in here? All right, we don't have any data. Yeah, so it strips all the extraneous information that you need. If you do objdump-d, it'll actually tell you all the instructions that are contained within the binary. When you create an ELF file, what it does is we'll get to this in a moment. Actually, I don't know if it'll be next class or the one after. But your binary is holding the information for your program, the instructions to execute, that are these things. You'll get to those instructions in architecture, by the way. It holds the instruction, which is the translation from your C code to what the CPU can execute. It also stores any static variables that you need for your program. It'll also store what the memory allocation, where to put all these variables. What debug does is it says, if your error was at this instruction right here, that maps to this C file at this line of code. And sometimes it'll also say it also maps to this variable in your C code as well. So when you do strip, you're getting rid of all of that inside of it. When you're doing, now you notice, you probably trying to point out that when you did strip, it actually got smaller than the regular one. There's other information it'll store in there, like this was compiled by GCC, whatever. Here's the author, here's the timestamp. It strips all that information out as well, so all you have is effectively the bare minimum in order to get the thing running. That statement is not completely true because there's other things you can strip out, but that's beyond the scope of this class. Great question. Any others? Okay. Adding optimizations. Did y'all turn on optimizations, or y'all never messed with that? All right. So the compiler can try and auto-optimize the code for you. Back in the 80s, this was basically a joke. But nowadays, it can make your program 3, 4, 5 times faster, not percent, by factor times faster, depending on many things that are going on in your code. There's a lot of things the compiler can automatically do for you, and even some things you're not going to be able to really do yourself that the compiler can do. And you enable different levels of optimization. Compiler optimization has come to the point where you have your class of optimizations that are a complete win no matter what, and then you have your class of optimizations that most of the time are helpful but may not be. So -O does the class of all the ones that are always a win, basically. -02 will do all the ones that we're pretty sure are going to do it and usually optimized for size. -03 is for GCC, basically adds all of them in. So you can do different levels if you want. For test, this is really not going to be much of a difference, but I'll go ahead and do it. Yeah, it's going to be the same size because there's not much to optimize with Hello World. I don't know what you'd be optimizing there. But when you start writing some of your other programs, I'll show you when you add optimizations on, it'll make a big difference. Okay. It is good to turn on WAL, which stands for Warnings All, when you're compiling. This I highly recommend you do. When you turn on this, you're telling the compiler, please tell me every instance where you think I might have an error. The compiler is actually fairly good nowadays about telling you, hey, look, I think you're writing past the buffer of this array. You may want to check this out, which will be very handy coming on later. And that's with -wal, although with GCC with Hello World, there's not many warnings you're going to get, so we will get to that as well. But let's go over to C++. All right, in C++, how did y'all print? Was it C out?
Yeah.
Okay, so let's go do that. Let's see, we go include IO stream int main int argc char star. And you could put the inline, but I'm not going to. cpp-o test.exe.cpp. Oh, that took a lot longer. All right. Hey, look, the CPP executable is bigger. Whatever. Hello, slightly. All right, so we have test.exe.cpp, and we can go ahead and try and run it. There it is. All right. Same thing, just you're using G++ instead of GCC. If you try and use GCC, let me show you what happens. Yeah. Undefined, here's the part that's going to be the kicker. Undefined reference to basic O stream. If you see that, you ran the wrong command. The rest of that, don't worry about that. Actually, undefined reference to std out, well, that may or may not be a problem depending on whether you included IO stream or not. So you could see that, but you forgot to include it. All right. Ooh, compiling multiple programs. All right. Did you do all your assignments in one file? Yes, no, maybe. When you did your programs, was it one file and you submitted one file? Or did you ever?
Sometimes we have multiple.
Okay, so you did do multiple files. Which one was that?
Oh, no, I'm talking about object-oriented. No,
That's fine.
C++, it was only one.
Okay, but in Java, you did have multiple files that you committed?
Yeah.
Okay, great. Good. So C++, there we go, supports that as well. So you can, or you are allowed to have different files. So let's go ahead and set that up. Well, it's going to be a little different. Let's go and do main.c. Let's see. Actually, we'll just do this. I have to spell main correctly, of course. Function 1. All right, well, that's not too helpful. So let's do a.c void function 1. So we'll define function 1 here. I'll go printf. I'll go ahead and include stdio.h. All right, and I'll go ahead and call function 2. And then I'll open up b.c. All right. What's going on? Well, main.c, just going to call function 1. That's at the bottom of the screen, so let me go back up here. Cat main.c, call function 1. A.c, call, actually prints function 1, then calls function 2, and then B.c is just function 2 calling out function 2. All right. So I put the code in 3 different files. Yes, this is a pretty small example, but this is just to show you how you can compile each one. Did I call them C files? I did. I meant to call them CPP files, but that's all right. We'll just do this main.c, A.c, B.c, and I'll put it out to main. Ooh, function 1 is not declared in this scope. Yep, that's a problem. So, in C++ and in C, you can't just call the function. You actually have to declare it. You may not have to implement it, but you do have to declare it. So the way you do that, we'll open up main.c, and we will declare the function right up there. Okay, you did not have to do this in Java. Did you have to do this in procedural ever?
Sort of, yeah.
Sort of, okay. What this is saying is, all right guys, look, there's going to be a function called function1. We'll define it at some point of time, but this is what it looks like, Stephen. It doesn't take any parameters and it doesn't return anything. It's going to exist at some point. Why do you have to do this in G++ or in C, and C++, but not in Java? The reason for that is C and C++ are single pass compilers, which means that they don't have the information yet about the functions, so you must declare it. Java is a multi-pass compiler where it scans your code first to identify all the functions and all the classes, then it goes back and actually tries to compile it for you. C and C++ are not. Anyone would take a guess why that's the case? Why is C and C++ one pass and Java's two pass?
One pass makes it run faster, two passes better for marketing.
Right, so two pass will take longer. Why, okay. So there's a performance difference, but the two pass is making it more convenient, right? Yeah. But does it really matter nowadays that much? Probably not. But then C came out in 1970 where it mattered a lot. So this is a bit of an artifact from back in the day. I do believe they should try and fix this, but I don't think they're going to because of how much code has already been written. But yeah, so compiling on GCC or single pass compilers is faster. So that's why you have to do this. So I wrote it in main.c. If I do this again, hey, the error about main.c went away. Notice up here main.c. There we go, main.c line 5. But now a.c line 5. Same problem. Well, I'm lazy, so I'm going to go here, copy it, go over to a.c, and paste it, and then change it to a 2. Perfect. And now if we compile it, hey, now we've compiled it all together, so I can go ahead and run function 1, function 2, and that's a general way of doing or compiling all your different by C files or CPP files into one. Okay, how are we doing? All right. So before we get too far here, into here, before we get to make files, one last thing. Inside of large programs, it would be very frustrating if you had to recompile every single file. Even with our faster computers, it would take not forever, it would take an incredibly long time if you had to recompile your every project every time you ran it. So all languages have something along the lines of doing a partial compilation so that you only need to edit the file that you need and then you compile that at the last moment. The way C or G++ does that is you do tac-c, which will make an object file. So, doing ls, we have main, and notice we have .c. Let me clear this and come back up to the top. If I want to just do a simple compilation into an object file of main, I would do tac-c. Now, before I do this, let me show you one problem. If I try to compile GCC and run this command, what do you think is going to happen? I'll go and use G++, so we can start getting used to that.
It doesn't see function 1 or 2.
Right, and so it's going to give us an error. Undefined reference to function 1. Oh, that's kind of cute. All right. But if I do this, okay, it's fine. What happened? Well, what it did is it just compiled the main.c file and did not try to produce an executable. It just did the compilation part. You can actually see this because if I do an ls, there is now a main.o file. I wonder what that is. File main.o. Relocatable, not stripped, elf64. All right, so this part basically is telling you that it is compiled code. It's an object code. So it's just the compiled part of main.o. if I were to try and finish the compilation, aka link main.o, that's when it would give me an error that function 1 is not defined. If I were to try and edit main.o, I'm just going to cat it. Hopefully this doesn't mess up my screen. It's definitely not C code, right? It's something else. It's actually binary code because I can do an obj dump -d main.o, and there's all the instructions inside of it, or the disassembly of it. So it is actually binary code to be run, but it hasn't been put together yet. Why is that important? Well, we can do the same thing for a.c. Oops. And then do the same thing for b.c. Now if I were to do .o, now we have the .o files for each one. Again, if I do file on a.o, it's an object file, b.o is an object file as well. All right. How are we doing? Following so far? What's missing?
No.
No. You're shaking your head.
No.
Oh, not you, sorry.
I mean, I'm really lost in general.
Okay, well, if you got a question, please stop. Please ask. You got a question, or we can do it during lab time if that helps.
Yeah.
Okay, that's fine. All
I
right.
don't know about that.
Sure. So let me clear this. ls star o, g++ star dot o. So now, if I want to do the compilation, I can, or not the compilation, what we're actually doing is called linking. I want to link all the object code together because it's already been compiled to an object code. I can, g++ will do that for me. Back in the day, you'd have to run a separate program. Things are a little better nowadays. We'll just have g++ link the .o code together because g++ will find out, oh, this is just object code, and then it actually produced an a.out for us. Let me go ahead and remove this. A.out, g++ star.o, and we'll output it to main, and then we'll call main. All right. All right. So there we go. We talked about compilation, multiple files, compiling them together, a little bit about how you link all that together with the declaring the function headers up here. We're going to do many more examples of that throughout this course. So this will come up again. And then we talked a bit about how to compile each file individually and link it all together. All right, any questions about that? Pause here.